Today we're doing something audacious. We're going to build a working interpreter for a small subset of Python, entirely in Java. Not a wrapper around an existing engine, but a real interpreter with a handwritten lexer, an abstract syntax tree, and a recursive evaluator. By the end, you'll understand how a high-level language tokenizes source code, builds a tree of statements, and executes them one by one. This isn't just a toy. It's the same pipeline used by CPython, JavaScript v8, and almost every interpreter you've ever used. We'll walk through every piece and explain exactly why each part exists. Every interpreter begins by deciding what atoms its language can contain. We create an enumeration called token type that lists every possible kind of token: numbers, strings, identifiers, keywords like if, else, while, and print, arithmetic operators, comparison symbols, the assignment sign, parentheses, and the colon that Python uses to open a block. We also include special tokens for new lines and indentation changes, because our little language is going to be whitespace sensitive, exactly like Python. Each token carries a type and sometimes a value. For example, a number token stores its numeric string, and an identifier token stores its name. This small token class is the first building block of our pipeline. Everything that follows will produce and consume these token objects. The lexer is a simple state machine that reads the source code character by character. It maintains a position counter, a current character, and also tracks the line and column numbers. When we call advance, it moves the current character to the next byte in the source and updates the line count if it hits a new line. This loop is the heartbeat of the lexer. The main method, nextToken, is responsible for looking at the current character and deciding what kind of token it should produce. When the lexer encounters a digit, it switches into number mode. It consumes as many consecutive digits as it can find and packages them into a number token. This is a very simple integer recognizer, no floating point, no signs, just positive integers. Strings are similar but more subtle. When it hits a single or double quote, it remembers which quote character opened the string, then consumes characters until it finds the matching closing quote. Along the way it doesn't handle escape sequences yet, but the basic idea is solid. Finally, when the lexer sees a letter or underscore, it switches into identifier mode. It gobbles up letters, digits, and underscores and then checks the resulting word against a list of keywords. If the word matches if, else, while, or print, it returns the corresponding keyword token, otherwise it's an ordinary identifier. This is exactly how most languages tell if from my_variable. After handling literals, the lexer still needs to deal with the language's punctuation. It examines the current character and produces a single character token for, dash, forward slash, parentheses, and the colon. But it also handles multi-character operators like equals equals, equals, equals. For instance, after consuming an equals, it looks ahead. If the next character is another equals, it produces an equality token instead of an assignment. This is called look ahead and it's a common technique in lexers. For any character that isn't recognized, a $sign, a %, the lexer throws an error with the line and column information, which helps the programmer debug syntax mistakes. This defensive approach means that later stages of the interpreter can assume the input is well-formed. Python's most distinctive feature is indentation-based block structure, and we want our interpreter to feel the same. The indent processor class is a wrapper around the lexer that consumes raw new line and space tokens and translates them into indent and dedent tokens that the parser will understand. It maintains a stack of indentation levels, starting with 0. At the beginning of each logical line, it counts how many spaces the line begins with. If the new indent level is greater than the top of the stack, it pushes the new level and emits an indent token. If the level is smaller, it pops levels and emits dedent tokens until the stack matches. This is a lightweight way to handle Python's whitespace rules. The actual code for this section is incomplete because it requires tight integration with the lexer, but the algorithm is well known and is exactly how Python's tokenizer works. Once we have a stream of tokens, we need to parse them into a structure that represents the program's logic. We define a hierarchy of AST node classes. At the root is an abstract AST node. Concrete subclasses represent numbers, strings, variable references, binary operations, assignments, if statements, while loops, and print statements. For example, a binary operation node stores the left and right sub-expressions and the operator token. An if node holds a condition expression, a list of statements for the true branch, and an optional list for the else branch. This tree is the intermediate representation between the linear source code and the evaluator. It completely captures the program's meaning without worrying about syntax details like parentheses or keyword order. Every language uses a similar tree representation before execution. Programs need memory. Our environment is a simple map from variable names to values. The values are stored as Java object references so we can hold both integers and strings. When the interpreter sees an assignment, it updates this map. When it encounters a variable name, it looks it up. If the name isn't found, the evaluator throws an undefined variable error, mimicking Python's name error. This environment is flat, there are no nested scopes or closures, but it's enough for a simple scripting language. In a full implementation, you'd chain environments together to support function calls and local scopes. Our tiny version keeps things simple while still illustrating the concept of a runtime symbol table. The evaluator is the core of the interpreter. It's a recursive method that takes an AST node and returns a Java object. For literal nodes, it simply returns their stored value. For a variable node, it delegates to the environment. For a binary operation, it recursively evaluates the left and right sides, then applies the operator. This is where dynamic typing happens. We check whether the operands are integers or strings and perform the appropriate operation. Integer arithmetic uses the familiar plus, minus, multiplication, divide, while strings support concatenation within basic comparisons. The evaluator also handles print statements by evaluating the inner expression and sending the result to system.out.println. This recursive approach is elegant and mirrors how expression evaluation works in many real interpreters. Although we haven't written a full parser in this code snippet, we've built the entire backend that a parser would target. A real parser for our tiny Python would consume the token stream and recursively build the AST. For assignments, it would see an identifier followed by equal symbol, then parse an expression and wrap them in an assign node. For control flow, it would consume the if token, parse the condition and the colon, then parse the indented block as a list of statements, maybe followed by an else. The parser would handle operator precedence by building up a binary expression tree using recursive descent or the shunting yard algorithm. Our evaluator already knows how to walk these nodes. The missing piece is just the parser, which is a mechanical but straightforward component of any language front end. In our main method, we show a sample program written in our mini Python. It assigns two variables, compares them with an if statement, runs a while loop that counts down, and prints several messages. The program is stored as a multi-line string. The message mini Python interpreter core is ready confirms that the evaluator, environment, and AST are all in place. To make it actually run, we would need to connect a lexer that handles indentation, a parser that builds the tree, and then feed it to the evaluator. But the intellectual heavy lifting is done. The architecture is complete, and the code illustrates every major concept of an interpreter: tokenization, tree representation, environment-based execution, and recursive evaluation. We've journeyed through the inner workings of a programming language, from raw text to execution. You've seen how a lexer carves characters into tokens, how an AST captures structure, how an environment stores state, and how an evaluator walks the tree to produce results.